Today I will start a new topic called binary decision diagram, or in short BDD. Okay, what we have seen till now, that we have seen about the verification of a system. For that we need to have a model of the system and we need a specification language. So, we are talking about CTL, computational tree logic, to given our specification, and we have taken our model as a finite state machine. Okay. Now, after that we have discussed about the CTL model checking algorithm. Now, if we give a model of our system and if we give a specification, then we apply our model checking algorithm to check whether the given specification is true in our system or not. So, if you look into this particular model checking algorithm, you will find that this is somewhat similar to a graph traversal algorithm. Okay. So, we traverse the entire graph and we will check whether it is true in some state or not. And ultimately, the model checking algorithm returns the set of states where the formula is true. Again, when we have discussed this particular model checking algorithm, we found that we are having a polynomial time algorithm to do the CTL model checking, which is polynomial in the size of our Kripke structure. This is basically polynomial in the size of the graph state space that we are giving into it, and also it is in the polynomial in the size of our given formula or the length of our given formula. So, we have seen that we are having a polynomial time algorithm and we are having an automatic methodology, automatic algorithm. We can develop this algorithm, we can implement these things, and automatically we can check whether a given formula is true in a given model or not. Manual intervention is not required. So, we are happy with that. But we have one more problem with this particular model checking algorithm. This is known as your state space explosion problem. What is this state space explosion problem? Basically, you just see that if we are working with a system where we are having n control variables, okay. So, or n control signals, that means those n control signals can be treated as our atomic proposition. So, number of different combination will be your 2 to the power n. So, for n signals, state space is your 2 to the power n, because we are having 2 to the power n different combinations. Now, say while we are designing it, first initially we have started with n signals, but we have found that it cannot be designed properly. We need one more signals. So, we will incorporate one more signal in our design, and eventually the total number of signal will become n plus 1, and state space will become now 2 to the power n plus 1. So, in this particular you can see that the state space is in exponential in nature. That means, it exponential to the number of signals that we have. So, for a smaller system it is fine, but for a bigger system it is going to give us problem. So, that is why we are now looking into some other way to represent our system. So, for that BDD is one solution. With the help of BDD, or we can tackle this particular state space explosion problem. Okay, now, that is why we are going to talk about BDDs. Okay, what is BDD? It is a binary decision diagram, which is a data structure to implement or to store any Boolean function. So, if we are having a Boolean function of 3 variable x, y, z, then function x, y, z can be represented with some Boolean expression, say x bar y plus y z plus z x bar. So, if we are having such type of Boolean expression, then this Boolean expression can be stored or represented with the help of binary decision diagram. So, we are going to look into this particular binary decision diagram in this particular module, and later on we are going to see how the finite state machine or the state transition graphs will be implemented or represented with the help of BDD, and we will see how the model checking algorithm can be incorporated for BDDs. When we use BDDs for our model checking algorithm, then we say this is your symbolic model checking. So, eventually we will go to symbolic model checking algorithms, where the system will be represented with the help of BDD, binary decision diagram. What is your BDD? So, I have already mentioned that BDD is used to represent any Boolean function. So, it is basically BDD is based on recursive Shannon expansion. We know that any Boolean expression can be expressed as a Shannon expansion. So, this Shannon expansion is given it like that, f is equal to x dot f x plus x bar dot f x bar. So, what does it mean? So, x is a variable. So, we are expanding this particular function on x, and we are having the evaluation value of x when we are going to treat x equal to 1 plus x bar, that means we are going to treat the variable x bar, and the functional value when we are going to treat this value variable x equal to 0. So, with the help of this Shannon expansion, we can represent any Boolean function, and the BDD is based on this particular Shannon expansion. What is BDD? It is a compact data structure for Boolean logic. So, eventually we will find that it is a compact way of representing our Boolean logic or Boolean function. On the other hand, we can say that we can represent our state space also with the help of BDDs, because state space can be represented with the help of a combination of some Boolean function. And one more advantage of BDD is that it is a canonical representation. So, it is reduced order BDDs are canonical in form. That means, we are going to get a unique representation of a Boolean function if we use ROBDD, reduced order binary decision diagram. First, we will talk about binary decision diagram, then we will go to order binary decision diagram, and finally, we will come to reduced order binary decision diagram. When we talk about reduced order binary decision diagram, you are going to get a unique representation of a Boolean function. That is why I will say that this is a canonical representation of a Boolean function. So, now I am going to give one example of this particular Shannon expansion. So, you just see that I am going to talk about this particular function f is equal to a c plus b c. Okay. That means, f is a function of 3 variable a c plus b c, and already I have mentioned that the Shannon expansion is your f is equal to x into f x plus x bar dot f x bar. That means, this f x says that the value of this given function when x equal to 1. So, this is basically we are going to have this function f. So, we are going to say f a will be the functional function when we are going to treat x equal to a equal to 1. So, f a will we are going to get as your c plus b c, because when we treat x a equal to 1, then 1 dot c will be equal to c plus b c. Similarly, f a bar is the function when we are thinking that value of a is equal to 0. So, f a bar is equal to f when a equal to 0. So, when we put a equal to 0, then these particular terms become 0, 0 plus b c. So, eventually we are going to get b c. So, f of a is your c plus b c, f of a bar is your b c. So, that is why this particular function can be represented as your f of a into b f a plus a dash into f of a dash. So, this is nothing but a into f of a is your c plus b c, and f of a bar is your b c. So, a bar dot b c. Now, basically what we can see that if we are going to just simply think that we are having these 3 variable a, b, c. Initially, we are going to look for the valuation of a. A can either take 0 or 1, just I am going to represent it something like that. So, this is the variable a. So, this may be your a equal to 0 and this is your a equal to 1. So, in this particular case already I have the valuation of a either a will be equal to 0 or a will be equal to 1. So, what we need to evaluate, this is a function based on this variable b and c, because already we have taken the decision on a. Now, this particular function that when a equal to 0, you see that the function will be your b c. That means, I am going to look about the function b c over here. So, I can say that this is your g, and when f is equal to s, and I am going to say that c plus b c is the value. So, I can say that c plus b c is the value, and I say that this is the function a. Now, my next term is to evaluate this function g and h. Again we will use this particular Shannon expansion. Say if you consider a variable b, then what will happen? I will take either b is equal to 0 and b equal to 1. Similarly, for h also we are going to talk about b is equal to 0 and b equal to 1, and eventually what function will remain? It will on the value of variable c. So, in this way recursively we are going to get Shannon expansion, and we are going to get a some sort of your decision tree or decision diagram, and it will be represented in this particular form. Now, we are going to talk about this particular BDD. So, binary decision diagram, but before going to binary decision diagram, I am going to talk about BDT, binary decision tree. So, it is a tree. So, we are saying that binary decision trees are trees whose non-terminal nodes are labeled with Boolean variables. So, if you are having a function of x, y, z, then non-terminal nodes will be represented by those particular Boolean variables, and the terminal nodes will be represented by the Boolean values or Boolean constant, either 0 or 1. So, when we are going to draw BDT or BDD, we use these particular circles to represent non-terminal nodes. And we use this particular square box to represent terminal nodes. Okay. So, in case of non-terminal nodes, it will be labeled with the variables of that particular function. Say if x is a variable, say I will label this particular non-terminal nodes with x. And if it is a terminal nodes, either Boolean functional value will be 0 or 1. So, I can say that if I write 1 over here, it says that this value of this particular terminal node is 1. So, we are going to draw a tree. In that tree, we are having terminal nodes and non-terminal nodes. The label of non-terminal nodes are the variables of the function, and the label of our terminal nodes are Boolean constant, either 0 or 1, which will be the functional value of the given function. Now, in BDDs or BDT, each non-terminal nodes are having two edges. Okay. So, if this is a non-terminal node x, it is having two edges. One edge will be represented by your dashed line, and second one will be represented by the solid line. The dashed line says that this is representing the valuation of x equal to 0, and solid line says that this is the valuation of x with value x equal to 1. So, I know that we are having only two possibilities, either x will be 0 or x will be 1. So, when I am going to treat the valuation of a particular variable x, then it is having two outgoing edge. The dashed edge basically says it is the value of x equal to 0, and x equal to 1 will be represented by this particular solid line. So, every non-terminal nodes are having two outgoing edges. Okay. Now, that is why you can say that. So, in our BDT we can write something like that. So, this is say variable x, this is variable y, this is variable z. So, when variable x equal to 0, we are having a valuation of x 0, then we are going to look for what will be the value of y. If value of x equal to 1, then we are going to say what is the value of y over here. Like that, we are going to construct the complete tree. It is a tree. Okay. Now, I am going to give an example. Just so that we are going to take a function f, which involve three variables. So, f is a function of these three variable a, b, c. All of you know that the Boolean function can be represented very well with the help of truth table. So, I can have this particular truth table representation of my Boolean function f, a, b, c. So, what you know is that it says that when a is equal to 0, b is equal to 0, c is equal to 0, then my functional value is 0. Similarly, if I say that if my a is equal to 1, b is equal to 0 and c is equal to 1, then my functional value is 1. So, in truth table we are going to represent all possible combination of these three variables, and you know that what will be the size of this particular truth table? It is 2 to the power n. We are having 2 to the power n entries in this particular truth table if n is the number of variables. So, here I am having 3 variables only. So, I am having 2 to the power 3, which is 8 entries. So, these are the 8 possible combination that we can have with respect to a, b and c, because A can take either value 0 or 1, similarly B and C. Now, this particular function I am representing with the help of your Boolean truth tables. Now, we can construct the BDD for this particular function BDT binary decision tree for this particular function looking into this particular truth table. So, if you look into it, eventually you are going to get that it is having these 3 terms. So, if you look into it, then eventually what will happen, 3 min terms will be there, and when I am going to reduce it, then eventually I am going to get this particular function f is equal to AC plus BC. Okay. Now, what we are going to do now, we are going to get the BDT for this particular function. So, this is the truth table I am having, this is the function f. Now, I am having 3 variables A, B and C. I have to see when A is equal to 0 and A equal to 1. So, when A is equal to 0, then I am going to look for this particular part, because A is equal to 0, now B and C can have value either 0 and 1. When A equal to 1, then I am having this particular part of the truth table. So, here I am representing one non-terminal nodes labeled with A, that means I am going to take a decision on A. When A is equal to 0, I will follow this particular dash line. When A is equal to 1, then I will follow this particular solid line. Okay. Now, when I am taking a decision on A, either I am coming to this part or this part. So, remaining portion will depends on B and C. Now, again when I will come to B, then B can be either 0 and 1, similarly B can be either 0 and 1. Now, eventually I am getting C. So, C will be either 0 and 1, since it is having only 3 variables. So, I have already taken a final decision. Now, I am going to represent those terminal nodes, which will talk about this particular functional values. Now, you just traverse one link, say when A is equal to 0, B is equal to 0, C is equal to 0, then my functional value is 0. So, that is why this terminal node is 1. So, when I say that A equal to 1, B is equal to 0, C equal to 1, then my functional value is 1, because it says that when A equal to 1, B equal to 0, C equal to 1, then this is the functional value 1. So, I am putting this 1 in this particular terminal node. So, you just see that by traversing all those particular edges, we can get the functional value of this particular Boolean function. So, that is why I can say that from truth table I can straightaway construct this particular BDT. Okay. So, this is the function f is equal to AC plus BC. If you reduce this particular representation, we are going to get this one, and this is the decision tree that we are getting over here. Now, you just see that we are having a truth table, I am getting an BDT, binary decision tree. What advantage we are getting by representing this particular truth table with the help of BDT? If you see, if you look into it, as such we are not getting any advantage. Because you see that when I am representing it with the help of truth tables, then what happens? I am getting total 2 to the power n entries if I am having n number of variables. Now, when I am drawing this particular BDT binary decision tree, again you will find that in leaf node or terminal nodes we are having 2 to the power n different terminal nodes, because this is going to give the functional values for different combination, and height of this particular tree will be n, basically level n, because we are having n variable. So, again the way we are having the exponential blow up in truth table, because if I increase by one more variable say d, then what will happen? We are going to get 16 different entries 2 to the power 6. For that also this BDT, the level of this BDT will be increased by 1, and we have to take decision on d, and eventually we are going to get 16 different terminal nodes. So, as such if you look into that binary decision tree and your truth table, we are not getting any advantage. In both the cases, we are having exponential blow up. So, that is why this is the just idea I am giving you, that how I am going to use this particular data structure to represent my function. So, instead of binary decision tree, we are going to look for binary decision diagram. Okay. Which is binary decision diagram? It is very similar to your binary decision tree, but now my representation will be a graph instead of a tree. I think you know what is the difference between trees and graph. So, we are going to get a graph now when we are going to talk about the BDD. So, this is a DAG, directed acyclic graph. So, because we are going to talk about the Direction also in this particular case, though explicitly we have not mentioned it, that means when A is equal to 0, I will follow this particular path, B is equal to 0, C is equal to 0, we are going to follow, and when C is equal to 1, we are going to follow this path. So, this is some sort of your directed graph. Now, that is why we are saying that what is your BDD? This is a directed acyclic graph, that means it is a directed graph, but it should not have any cycle. And a similar way, now we can talk about BDD also. So, what happens in BDD? We are saying that we are having terminal nodes and non-terminal nodes. In BDD also, we will be having terminal nodes and non-terminal nodes. In case of non-terminal nodes, that will be labeled by your Boolean variables. Terminal nodes will be labeled by Boolean values 1 or 0, and every non-terminal nodes are having two outgoing edges. One edge will be represented by your dashed line, and second one will be represented by your solid line. Dashed line says that the value of this particular value is taken as 0, and solid line says that the value of this particular variable is taken as 1. So, you just see that this is similar to your BDT only, but it is now we are going to get a graph instead of a tree. Now, what is the primitive of our BDD, primitive BDD or primitive binary decision diagram. So, in this particular case, we are going to get 3 primitive binary decision diagram, and with the help of these 3 primitive binary decision diagram, we are going to construct the binary decision diagram of any given Boolean function. So, this is your B 0, it is a terminal node labeled by 0, it says that the Boolean value is equal to 0. Okay, so, this is B 0 is representing this particular BDD, which represent the Boolean constant 0. Similarly, we are having one binary decision diagram BDD B 1, which represent a Boolean constant 1. That means, this is just a box written 1 over here. So, this is a primitive BDD, it says that this is the Boolean constant 1. B 0 says that this is the Boolean constant 0. And another BDD we are having, which represent the Boolean, any Boolean variable. So, if we label by x, then we are going to say this is the BDD for the Boolean variable x, and we say this is your Bx. So, what it says that x, it is having two outgoing edges, one dashed, second one is your solid. Dashed line is pointing towards the Boolean constant 0, and solid line is pointing towards the Boolean constant 1. That means, when x is equal to 1, then my functional value is 1. So, this is the representation or BDD representation of any Boolean variable x. So, these are the 3 primitive BDDs, and with the help of these 3 primitive BDDs, we are going to construct the BDDs of any given Boolean function. Now, just see that what I am going to talk about. Now, we are saying that the BDD is nothing but, or BDD can be constructed or represented with the help of Shannon expansion. Again, consider this particular same Boolean function f equal to AC plus BC, and the Boolean Shannon expansion is your f is equal to f of x f x plus x dash of f of x dash. That means, functional value of f when x is treated as equal to 1, and your functional value of f when x is equal to 0. That means, I can say that already I have said that f of a equal to 0 will be your BC, because a equal to 0 I am going to have BC. So, I said that this is your BC, and when f a is equal to 1, then f of a is your C plus BC, because a is equal to 1, 1 into C equal to C. Now, the functional value depends on C. So, C plus BC. So, one I am saying that this is a sub function G, and second is sub function H. So, this particular information we are going to represent with the help of this particular partial BDD. So, we are having a terminal nodes A, either A have value 0 or A have value 1. So, when A is equal to 1, then I am having the sub function that we have to evaluate is C plus BC, this is H, and when A equal to 0, then sub function we are having G, which is your BC. So, this is the partial BDD for this particular given function after taking the decision on A. Now, what we have to do next? Now, either we have to take decision on B or decision on C. Now, if I am going to take decision on B, then I am going to label these two things with B. Okay. So, in this particular case, now again I will apply this particular Shannon expansion for this particular function G or this particular function H. This way we can construct our BDD also. So, eventually now what will happen? You just see now we are going to apply this particular Shannon expansion for all the variables. So, we are getting g and h. Okay, here I will be having the function g and here I am having the function h. Now, we will apply Shannon expansion on g and h. So, if b equal to 0, then what will happen? The functional value is 0, and when b equal to 1, then g b will be your c, because if it is your b equal to 1 dot c will be c. Similarly, in case of h, if it is your b equal to 0, then it will be equal to c, and when b equal to 1, then it will be c plus c, which is equal to c. Now, you just see that now what we are drawing now, when b equal to 0, that functional value is 0. So, we are drawing this particular s and saying that when b equal to 0, functional value is 0. When b equal to 1, then functional value is c. So, that is why I am drawing this particular c, node c, and pointing from b to c with the help of solid line. Similarly, in case of your function your h, when b is equal to 0, the functional value is c. So, this dashed line is coming to c, and when b equal to 1, then again the functional value is c. That is why this solid line is coming to this particular node c. Now, we are having this particular 3 function, one is already getting the constant. Now, you shall see that these sub functions are depends on your c. If c is equal to 0, functional value is 0, c is equal to 1, that functional value is 1. So, for that from c I am having this particular dashed line which is coming to 0, and we are having this particular solid line which is pointing towards this particular terminal node 1. So, eventually I am getting this particular BDD. Okay. So, this is the BDD of this particular given function a c plus b c. Now, you just see what we have got now. We are taking this particular function f is equal to a c plus b c. So, from truth table I am getting this particular diagram which is your BDT, basically binary decision tree. Okay. And by using this particular Shannon expansion, I am getting this particular diagram. It is I am going to say this is your BDD, binary decision diagram. So, both these diagrams are now representing the same Boolean function. Okay, because you can traverse this particular graph and eventually you can find the valuation of this particular function. Say if a equal to 0, b equal to 1, c equal to 1, functional value is 1. So, when a equal to 0, b equal to 1, c equal to 1, my functional value is 1. So, from both this diagram we can see this. So, here we are having BDT and we are having BDD, but both are representing the same action. So, here I am going to get some sort of a compact representation of this particular given function. Okay, now, they are equivalent, both of them are representing the same function. So, whether can we achieve this particular BDD from this particular BDT? It may be possible. Just see what we are going to do. So, we can use some reduction rules, and with the help of this particular reduction rule, we can try to reduce our BDD or we can try to reduce our BDT. So, what is that reduction rule? First reduction rule, we are saying that eliminate of duplicate terminals. So, if we are having duplicate terminal nodes, we can eliminate it. Say if we are having more number of terminal nodes which are going to represent the Boolean constant 0, then we can represent those particular terminal nodes with one terminal nodes. If we are having several terminal nodes which are representing Boolean constant 1, we can represent those particular several terminals with the help of one terminals which will represent this particular Boolean constant. So, that is why the first rule we are saying that eliminate of this particular duplicate terminal. So, if we apply these things to our BDT, then what will happen? You just see. So, in case of these things, what will happen now? All terminals node will be combined to one and their incoming edges will be redirected to this particular new terminal nodes. Okay. Now, what happens? You just see that this is the BDT that we had. Now, we are having several terminal nodes, some are represented by zeros or some are represented by 1. Now, all zeros will be combined and represented by 1 terminal nodes, and all 1 will be combined together, they will be represented by 1 terminal nodes 1. And whatever incoming edges are coming to those particular terminal nodes, they will be redirected to this particular terminal node. So, after eliminating this particular duplicate terminals, what I am getting from this BDT, we are getting some sort of BDD over here. Okay. So, now at least we can see that the number of nodes are less here, because instead of 2 to the power n nodes, terminal nodes, we are getting only 2 terminal nodes. So, here we had 8 terminal nodes, because we are having 3 variables. So, this 8 terminal nodes will be represented by 2 terminal nodes. So, it is for any function. If we have a function of n variables, then in BDT we are going to get 2 to the power n terminal nodes, but in BDD we can represent these 2 to the power n terminal nodes by only 2 terminals nodes. So, there is a massive reduction. Okay. So, we need to have only 2 terminal nodes when we talk about BDD. Okay. This is one reduction rule, say eliminate of duplicate terminals. So, second reduction rule, we are going to say that eliminate of redundant nodes. That means, if with both edges pointing to the same node, we are going to see what we are going to talk about the redundant nodes. So, eliminate of redundant nodes. What we are going to say about these things now is just see that we are having this particular partial BDD. Just consider this one. So, we are taking some decision, we are coming to A. When A equal to 0, it is pointing to this particular non-terminal nodes. When A equal to 1, again it is pointing to this particular terminal non-terminal nodes. Okay. So, now you just see that when A is equal to 0, then 0 into that functional value depends on B. So, that is why I am saying that when A equal to 0, then A dash into G B, that remaining portion. Similarly, when A equal to 1, again we are getting that A dot G B, because already we know A equal to 1, and this is the remaining portion that we have to evaluate. So, this is basically what happens. You say that A dash G B plus A G B, which is equal to G B. That means, now you just see that whatever function that I am going to have, it is basically redundant or irrelevant on the decision of this particular A in this particular path. So, in this particular path, so that is why what I am saying that we are going to eliminate this particular redundant node. So, if we are having such type of redundant nodes where both 0 and 1 edges pointing to the same sub function, then we can eliminate this thing. So, we eliminate this particular nodes, and all the incoming edges will be directed to this particular node. So, in this particular way, we can eliminate some of the redundant nodes. Okay. After eliminating this particular redundant nodes, my size of your BDD will get reduced. Okay. That means, we are going towards the compact representation of our Boolean function. So, first reduction rule is your elimination of duplicate terminals. Second reduction rule is your elimination of your redundant nodes. Now, we may have one more rules, which is your reduction rule 3, which is nothing but called your merging of your duplicate nodes. So, if we are having some duplicate nodes, then we can merge them together, and we are going to get a some sort of simpler or reduced BDD. Now, you consider this particular partial BDD. So, what happens in this particular case? You just see that I am coming to this particular 2 nodes. Now, I have to take the decision on A. So, F A we are evaluating, and in this particular node I am going to take the decision on A. So, what will happen in this particular case? If A is equal to 0, then I am coming to this particular node B. When A equal to 1, I am coming to this node C. That means, this is A dash into G B. So, this is basically coming through this particular dash line is going to say A dash dot G B. And when I follow this particular solid line, then I am going to get A dot H C, that sub function that we are having in this particular node is your H. So, A dot H C. So, when I consider this particular node A, this particular node, I am getting this particular function. Similarly, I am coming to this particular node, and whatever we have evaluated over here is say F 2. Now, again you just see that when A is equal to 0, we are coming to the same node B, and when that means, we are going to look for the same function G, and when a equal to 1 we are coming to the same function h. So, in this particular case the partial evaluation of the given function for f 1 and f 2 both these functions are same. So, we are saying that f 1 equal to f 2 which is your a dash g b plus a h c. So, in this particular case we can say that these are basically some sort of duplicate nodes that we have in our BDD. So, what we can do now? We can eliminate these or merge these two nodes to a single node. So, in this particular case both f 1 and f 2 will be equal to your f. So, we can say that merging these two nodes to 1 and these are the sub function that we are having. When it is equal to a equal to 1 we are going to evaluate this sub function h, and when it is equal to 0 then we are going to evaluate this particular sub function g. So, like that we can merge this particular duplicate nodes and eventually we are going to get some sort of your reduced or compact representation of our given Boolean function. Okay. So, we can have these particular three rules. Now, you just see that first we are getting this particular truth table, we are looking into a function representing by truth table and we are drawing this particular binary decision tree from this particular truth table. So, it is having an exponential blow up. Now, what we are going to see, we are trying to reduce it. Okay. When we are going to reduce it, according to the first rule, we are going to merge the terminal nodes. So, we try to merge those particular terminal nodes. So, we are getting two terminal nodes, one is 0 and second one is 1, and we are going to redirect those incoming edges to these two terminal nodes. So, after application of first reduction rule, we are reducing the terminal nodes to only 2. Okay. So, we may have 2 to the power n terminal nodes in binary decision tree, but eventually we are going to get 2 terminal nodes in our binary decision diagram. With the help of first reduction rule merging of terminal nodes, we are getting only 2 nodes instead of having this particular 8 nodes. Okay. Okay. Now, next you just see that after getting this particular some sort of your reduction, now we are going to look inspect those particular nodes. Now, you just see this particular 3 nodes C. When C equal to 0, the functional value is 0, when C equal to 1, functional value is 1. So, nature of these 3 nodes are same. So, these are basically some sort of duplicate decision that we are having. So, in this particular case, we are going to merge these 3 nodes to one particular node C and the incoming edges will be redirected. So, from B it is 1 coming to C. So, B equal to 1 coming to C, B is equal to 0 coming to C, B equal to 1 coming to C. So, these are the two dashed line and S line. We are solid line. So, we are redirecting those particular edges. So, we are getting some sort of reduction over here when we are merging the duplicate nodes. So, by this particular reduction rule merging of the duplicate nodes. Okay. Now, so after that we are going to see whether we are having any redundant nodes or not. So, in this particular case you just see that if you look this particular node B, what we are getting when B equal to 0 I am coming to C, when B equal to 1 we are coming to C. That means, whether B equal to 0 or 1 it is immaterial, we are going to evaluate this particular sum function. Similarly, when I look into this particular C, again if C equal to 0 the functional value is 0, C equal to 1 functional value is 0. So, again it is immaterial on the decision of this particular C. So, what happens now? We are going to get this particular diagram BDD where we are removing these two redundant nodes. So, eventually we are getting this particular BDD. Okay. So, we have applied your this reduction rule, removal of your non-terminal nodes, merging of duplicate nodes and remove of redundant nodes. After removing of redundant nodes, it may happen that some duplicate node may arise again one here. So, what we are going to do? We will again apply this particular merging of duplicate nodes. After merging of duplicate nodes, what will happen? Again some redundancy may arise, then again we are going to remove those particular redundant nodes. So, in this way what happens? We are going to repeat this particular two rules and try to eliminate more and more redundant nodes and merge duplicate nodes. So, eventually we are coming to this particular BDD. Okay. So, you just see that this is what we have talked about here, that we are looking into the BDT and we are applying those particular reduction rules, and eventually we are coming to a representation, and you just see that no more reduction is possible, because A, B, C, these are the 3 nodes. There is no redundant nodes, because all zeros and 1 edge are going to different direction. We do not have any duplicates also, because the levels are different. So, since the levels are different, the question of duplication is not arise over here. Okay. Now, this is from BDT, we are coming to this particular reduced BDD. Similarly, we have the same function we have taken, and we have constructed BDD with the help of your Shannon expansion. So, this is we are constructing this particular BDD with the help of Shannon expansion. So, after constructing this particular BDD, we will see whether it can be reduced or not. So, first rule talks about the redundant removal of your terminal nodes. So, since we are using that Shannon expansion, so there will not be any redundant terminal nodes, because we are going to have only 2 terminal nodes. So, basically we have to look for the other 2 rules, merging of duplicate nodes and removal of your redundant tests. So, when I am coming to this particular diagram BDD, we have found that this particular node B, it is doing some sort of your redundant test only, because B equal to 0 and 1 is going to have the same sub function. So, we can remove this particular redundant nodes, and ultimately we are coming to this particular BDD. So, whatever you are going to do, if we are starting from your BDT, or you apply Shannon expansion to get your BDD, eventually we can apply those particular reduction rules, and finally we come to a particular BDD. Okay. So, we are coming to this particular BDD, and no more reduction is possible over here. So, by looking into these things, what happens? Now, we are going to have the notion of your reduced BDD, reduced binary decision diagram, which is written as your RBDD, reduced binary decision diagram. When we say that a binary decision diagram will be a reduced one, we will say that it will be a reduced one, okay, if none of the reduction rule R1 and R2, R3 can be applied. Okay. So, we are having 3 rules R1, R2 and R3. If none of this reduction rule can be applied anymore, that means no more reduction is possible. So, if no more reductions are possible, at that point we are going to say that this is the reduced BDD, we are getting it. So, we say this is RBDD or say reduced BDD. Okay. So, this is the notion. So, when we are coming to that reduced BDD, that means no more reduction is possible, and we are getting a representation of my given Boolean function. So, you just see that we are representing our BDD binary, representing our Boolean function with the help of a decision diagram, which is known as your BDD, binary decision diagram. It can be reduced to get a reduced BDD, and in reality we have found that in most of the cases we are going to get a compact representation of our Boolean function. So, initially what happens when you talk about BDT, you will find that we are having exponential blow up, we are having total 2 to the power n numbers of terminal nodes if we are having n variables. But we can apply the Shannon expansion also to construct a BDD for a given function. When we are using the Shannon expansion, at least we can assure that we are going to get only 2 terminal nodes, and we may have some non-terminal nodes. When we are getting the initial BDD with the help of Shannon expansion, then we try to use the reduction rule, removal of your redundant test and merging of duplicates non-terminals. By repeated applied of these 2 rules, we are going to get a compact representation of our given Boolean function. So, when we are having a compact representation of our Boolean function, we are going to use these things while representing our Boolean function, and it is going to help us to tackle with the state space explosion problem. We will see how we are going to represent our state space with the help of binary decision diagram. So, basically we are going to have say if I am going to have any Boolean logic circuit, just for explanation I am saying that I am having 2 AND gates over here and 1 OR gates, that input variables are your A, B, C, D. So, if it is the 4 input variables, and if this is the circuit given to me, then what happens? I can write the function for this particular function is your, this is nothing but sum of product. That means A into B plus C into D. You just see that if we are having any Boolean circuit, any logic circuit, we can always write the Boolean expression for this particular circuit, and once we have this particular Boolean expression, then what will happen? Always we can try to construct the BDD for this particular Boolean function. Okay. You just say once we are constructing the BDD, then we can use those particular BDD in our work. Okay. Now, you just see, now we are having some BDD, just we are representing this particular BDD, something like that in symbolic way. This triangle we are writing that this is the BF, BDD of the Boolean function f. Just look into the previous example, say I am having say A, either this is B, if B equal to 0, then I am having the functional value as 0. If B equal to 1, I am coming to C. If A equal to 1, C is equal to 0, functional value is 0, and C equal to 1, my functional value is 1. So, this is the BDD that already we have seen, that is a simple BDD. Now, this particular tree generally we represent with the help of this particular triangle, and we say that this is the function BDD for function BF, and eventually it is having this particular two terminal nodes, either 0 and 1. So, this is basically we are representing binary decision diagram BF. This is the graph that we have, and eventually we are having these two terminal nodes. So, if we are having a BDD of BF, then we can do some of the operation on this particular BDD also. Now, you just see that if I am having a function BF, say f, I am having some function, then the complement of f is your written by your f bar. Okay. Now, if the BDD of this function is your BF, then I am going to get the BDD for this particular complement of this function BF prime. Now, if we are having the BDD of a particular function, to get the complement is very simple, because we know that if it is complement, basically if x is equal to 0, then complement of x is 1, if x is equal to 1, then complement of x is equal to 0. So, what we are going to do? Simply we are going to interchange these two particular terminal nodes. So, if it is 0, then 0 will be replaced by 1 and 1 will be replaced by 0. Okay. So, this is the way that we can say that if I am having a given Boolean function, if we know the BDD representation of this particular Boolean function, then complement can be very easily find out. Okay. What? Just simply interchange the terminal node, 0 will be replaced by 1 and 1 will be replaced by 0. So, this is very simple. Secondly, if we are having some Boolean function, generally then what we are going to do? We are going to perform some Boolean operation also. Say if I am having one function f and one function g of the same variable of different variable, then what happens? I can perform Boolean function f plus g, or I can perform Boolean function f dot g. Okay. So, one is conjunction, second one is disjunction. Now, say if I am having two Boolean function, we can do it. If I give any two Boolean function to you, always you can find out the sum of these two Boolean function or product of this Boolean function, disjunction and conjunction. Now, if I give you the BDD representation of these two functions, instead of giving the original function, I will give the BDD representation of these two functions. But can you construct f plus g or f dot g? Again, if you look into it, these are very simple way you can do it. You just see that this is basically representing f plus g, that first diagram. Why I am saying that this first diagram representing f plus g? Because f plus g, if you say that if anyone is 1, then output is 1. So, first I am evaluating g, this is your evaluating f, this is your BF. If f is equal to 1, then what will happen? F plus g will be 1. So, if f is equal to 1, I am just taking this decision, my functional value is 1. Now, similarly, if now f is equal to 0, so 0 plus g. So, this is basically depends on g. If g is equal to 1, my functional value is 1. So, g is equal to 0, my functional value is 0. So, that means in this 0 terminal node, just I am going to plug in this particular BG. So, this particular whole diagram is going to give me f plus g. So, just see that construction of f plus g is also very simple. So, f dot g is other way around. If f is equal to 0, then the value of f dot g will be equal to 0. If f is equal to 1, then the functional value will depend on your value of g, because f dot g, f is equal to 1, 1 dot g. So, basically if g is equal to 0, then my value is 0, if g equal to 1, my value is 1. So, that is why now what I am doing, first b f is representing this particular Boolean function f. If f is 0, so this is the result, my functional value is your 0. If f is 1, then what happens? I am going to look for the value of g. So, I will just simply plug in this particular BDD of Bg for function g in the one terminal nodes of this particular BF, and eventually it is going to give me this particular. And later on what I can do, again since I can say that these two can be merged. So, that means I can redirect this particular s to these things, and I can redirect this particular s to this particular. Again, after having these two BDD, we are getting an BDD. If required, I can go for reduction of this particular BDDs also. Okay. Now, you just see that we have seen one particular data structure known as your BDD, binary decision diagram. We can represent our Boolean function with the help of your BDD, binary decision diagram. And I have mentioned that from result also we have found that in most of the cases we are going to get a compact representation of any given Boolean function. Now, just look for some questions, very simple question I am giving it to you. First question I am saying that do you get any advantage in using BDT, binary decision tree? So, we are saying that we are going to look for a data structure which is going to give us a compact representation of your Boolean function. I have mentioned about BDT, binary decision tree. Now, whether do you get any advantage of your BDT? So, if you look into it, the construction of BDT and the BDT that it looks like, as such we are not getting any advantage. Why? Because it is simple mapping or simple transmission of my truth table to BDT. In truth table, we are having a problem with your exponential blow up. If I am having n variables, I am going to get 2 to the power n different entries. So, in BDT also, we are going to get 2 to the power n terminal nodes, and where the label will be is equal to your n. So, as a simple example, you see that if I am going to have a function which is having 8 variables, then the total number of entries in our truth table will be your 2 to the power 8, which is your 256. When we are going to look into the BDT, we are going to get 256 terminal nodes, and the label of this particular BDT will be 8, because for each variable we are having one label. So, as such we are not getting any advantage, but for clarity just I am mentioning what is BDT, and but from BDT we can use the reduction rule and we can get the BDT. Now, second question, you just see that while constructing the BDD, is it required to start from BDT? Again, I think it is very simple answer. You will, after listening to my lecture, you can very well say that this is no, because BDT can be again viewed as a repetitive application of our Shannon expansion. Okay. That means, one way we can construct the BDT and apply the reduction rule. We are having 3 reduction rule. This is your eliminate of terminals node, duplicate terminal nodes, removal of redundant edges, and merging of your duplicate non-terminals. Okay, we can apply those things and we can find out those particular BDT or reduced BDT. On the other hand, we can use the Shannon expansion. Repeatedly, we are going to use this particular Shannon expansion on each variable, and we can get the initial BDT. So, after application of Shannon expansion, whatever BDD we are getting, it may not be a reduced one, but of course, we are having only 2 terminal nodes, one representing the constant 0 and second representing the constant 1. So, after getting this particular binary decision diagram, we can apply the other 2 reduction rule. One is your removal of redundant test, and second one is your merging of duplicate non-terminals. So, repetitively we are going to apply these particular rules, and finally, we are going to get a reduced BDD. When we said it is reduced BDD, when none of the reduction rule can be applied further. Okay. Now, third question, you just see that the definition of BDD does not restrict the occurrence of a variable in any number of times in a path. Okay, so that it may lead to inconsistency with an example. Now, you just see that we are defining the BDD, binary decision diagram, or reduced binary decision diagram. and when we are defining it, we are saying that it is a DAG, directed acyclic graphs, which is having non-terminal nodes and terminal nodes. Non-terminal nodes are having, or it is labeled with your variables, and terminal nodes are labeled with constant 0 and 1. And every non-terminal nodes are having two outgoing edges, one is representing 0, which is given by dashed line, and second one is representing the value 1, which is given by the solid line. Now, I am saying that since this is the definition of BDD, so it is not restricting us to use the same variable in many different places, okay? And they can come in any order and they can come in any. So, if we use this particular basic definition and we can construct whether it is going to give us any problem, if it is going to give us any problem, then show it with an example. So, now what I can say, okay, now I will just say draw one particular BDD. So, this is your x, x equal to 0 and x equal to 1, I am getting y. So, if y is equal to 0, say I am having this functional value 0. If y is equal to 1, say I am drawing something like that x. So, I can draw this particular BDD. As per our definition of BDD, it is a correct BDD. So, I am having 4 non-terminal nodes, every non-terminal nodes are having 2 outgoing edges, I am having 2 terminal nodes, and that non-terminal nodes are labeled with the variable x, y and z x. Okay, we are having it is a function of 2 variables x and y. So, now you just see that in this particular case, when x equal to 0, y is equal to 0, my functional value is 0. That means, x bar, y bar is equal to 0. When x equal to 0, y equal to 1, then what will happen? Again, I am going to take decision on x. If x equal to 0, then I am going to get 0, and when x, y, when x equal to 1, then I am going to get 1. Now, you just see that in this particular case, I am having x bar, y, x bar is 0. Basically, I am looking for this particular execution part or this particular part valuation, actually x equal to 0, y equal to 1 and x equal to 0. When I look into this particular valuation, basically I am looking at valuation of x equal to 0, valuation of y is equal to 1, value of x equal to 1. Now, you just see that in this particular part, the valuation of x is taken as 0 as well as 1. But you know that if we are going to consider any Boolean function, if you look into any Boolean variable, at any instance of time that Boolean variable can take only one value, which is known as your one value, it is either 0 or 1, but it cannot take both the value 0 and 1 together. So, if you look into this particular part, what will happen? The value of x is taking 0 as well as 1. So, this is basically inconsistent. We are getting an inconsistency. So, we are having an inconsistent part in this particular representation. So, though our basic definition is of BDD is not restricting about the occurrence of variables in any number of times in any places, but we may face problem. So, in that particular case, what happens? We have to come up with the notion of your consistent parts, and when we are going to look for the evaluation of this particular Boolean function, it should be evaluated through the consistent part only. We should not evaluate it through inconsistent part. So, that is why we are having this is as one inconsistent part, because here x equal to 0 and x equal to 1, which is inconsistent. Similarly, we are going to get another inconsistent part, x equal to 1, y equal to 0 and x equal to 0. So, here x equal to 1 and x equal to 0. This is also inconsistent. So, we cannot have any valuation through this particular part. Okay. So, this is the problem that we are having. So, if we look into the basic definition of BDD, then valuation of this particular Boolean function have to be done over consistent part only. So, this is a consistent part, we do not have any problem. X equal to 0, y equal to 0, we are going to get this particular value. Okay. Similarly, this is also another consistent part, x equal to 1, y equal to 1, we do not have any. So, evaluation have to be defined over consistent path, we may have inconsistency. Another question we are talking about is reduced BDD of any function is unique. So, we are talking about BDD, we are going to get the after application of reduction rule, we are going to get the reduced BDD. Now, whether the reduced BDD representation of any function is unique, as if you look into it, let us see. So, this is the function that we are talking about, f is equal to a c plus b c. So, a, b, c, and I am getting this particular BDD, and no more reduction is possible. So, it is a reduced BDD of the given function. Now, the same function I can do in another way. Okay. Now, what will happen? Now, here what we are doing basically, we are applying this particular Shannon expansion in different way. First, I am applying this on particular variable b. So, this is b. After taking the decision of b, I am going to take the decision on c. That means, I am using the Shannon expansion on the variable c, and finally, we are going to apply the Shannon expansion on a. So, you just see that now I am having b, c, a. So, this is another reduced BDD. Okay, on this particular 3 variable a, b, c. Now, again you just see that I think it is a reduced one, you cannot apply any more reduction in this particular thing. So, we are getting reduced BDD. So, same function I am taking, f is equal to a c plus b c. Okay, I am getting one BDD this way and another BDD what I am getting a b. If b is equal to 0, I am going to get 0. If b is equal to 1, it depends on c, and 1, c is equal to 0, and so these are the two RBDD, both are representing the same function f is equal to ac plus bc. So, that means, what we can say that the BDD representation or reduced BDDs are not unique for a given function, and from this we have seen. But here is a crux, we have seen that the order, the Shannon expansion that we have used for constructing this BDD is in the order of a, b, c in the variable, and here we have applied the Shannon expansion on the variable in the order b, c, a. Maybe due to this reason we are getting different representation. Okay, in next class we are going to talk about those particular issues about the ordering of this particular variable. Okay, but is just see that if you simply talk about BDD and if you talk about RBDD, reduced binary decision diagram, then this is not unique. This is one simple example I am giving. Okay, I will stop here today.